let's get moving. Alright. Looking good. Alright. So. Yep. Hello everyone and welcome back to C Mathematics. We're going to be doing another hash algorithm today. It's going to be the second version of the secure hash algorithm, SHA2. We're going to be looking at how similar in structure it is to SHA1, but how it does also provide a lot more sorry, I'm listening to my voice. A lot more there's a lot more security features that you will find in SHA2, and that's why it was accepted as an improvement to SHA1. Okay. So, let me go to my desktop, and we're gonna go back to SHA1 just to do a quick recap of stuff, and then we will then implement it. But once again, I'm literally going to reuse these notes from SHA1 just because the high level structure is the exact same. It's just the functions are a bit different, at least for SHA224 and 256. So SHA2 is, like I said, the second evolution of SHA, or the first evolution of SHA1, and it operates in pretty much the same exact way, except the round. We're going to see that the round constants are different. The algorithm used to shuffle around data is different. And then also the biggest improvement is that it offers different security levels. So we saw that with SHA1, the default output size was 20 bytes, and that was it. So there were 2 to the 20, which is still a lot, possible values that a hash could take on. But with SHA2, there are 4 different security levels. There's SHA224, 256, 384, and then 512. And you can increase the security level if you want to have more possible values for the hash, which is, as we've looked at before, makes it more secure because there's less chance of getting a collision in the there's less chance of getting a collision. So what this will do is that we can, it's kind of like SHA3 and how we you saw that by changing the security level, you would decrease the bit rate, which would increase the randomness, or not the randomness, but increase the number of rounds that you would have to do for a message, which would make it more secure. So let's look at the high-level structure of SHA2. So I'm on the SHA1 document because it's gonna be the exact same. So the pre-processing bit of SHA2 is the exact same for SHA224 and 256. I'm just going to be doing that for now, but I will put a side note later on what is different about SHA512 and 384. So for 224 and 256, we see that our message is going to be broken up into blocks as with SHA1 and all the other hash algorithms. We're going to have blocks of 512 bits, and the last 64 bits are going to be the length. So we have our n-bit message, so I'll just zoom in a lot here. So we have our message, which is going to be n bits, so I'll just draw here, so the message goes to here. That's the message, and then we're going to pad it so that we get a complete block of 512 bits. Now the first part of the padding is just padding to some multiple of 512 minus 64 bits. So we're reserving the last 64 bits for the size. So the way we're going to pad before the size is just a 1 with a bunch of zeros, like that. So that's the 1 and zeros, and then we have 64 bits for the size. So we see this example here. If we have this message ABCDE, we see the hexadecimal values here where we have the 5 characters are put A, B, C, D, E, and then we have our 80, which is just the first bit 1. That one right here. Just clean this up. And then we go all the way down, and then we have our last 64 bits for the size. Now for SHA2 and 512, the difference is that we're going to have a block size of 1024 bits. So rather than having a 64 byte block size, we're going to have an 128 byte block size, which will increase the memory that we're going to need. And also it doubles the reserved size for the message length. So instead of having only 64 bits, we're going to have 128 bits for the message length, which may become tricky when we have to store the message length, because there's no value that's going to be 100. There's no word in C that's 128 bits. That's just like native to all machines. So what we're going to do is we're going to store an array of 2 unsigned long longs. All right. So that's the pre-processing, and then once again the high level. I'll actually just copy this over to. So yeah, once again we do our pre-processing, the padding. So we have padded our message over here. I'm looking over here. Once we have padded our message, then we split it up into blocks of 512 bits. Once again, this is for 224, 256. And then we pass it through our initial values. Now our initial values are we're not only going to have 5 integers, we're going to have 8. So it's going to be H5, H6, H7. And then we pass these initial values through the SHA2 function, which is going to look the same for all of our security levels, all 4 of them, except for 224 and 256. We're going to have different rotation constants, so we're just going to split it up into 2. Well, we're going to do our SHA2 function in 2 different implementations. One will be for the 224 and 256 bit, and then the other one for the 384, 512. And one of the main differences is the rotation constants that we're going to be using, and we'll see that later on, but also word sizes. So since we're doubling up the block size, we're going to, instead of storing these initial values as integers, for 384 and 512, it's going to be 64-bit words for the hash, for the output hash. All right, but we're looking at 224 and 256 now. So we just have integers here, 8 integers. They have some initial value, and those initial values will differ based on 224 and 256. And then the output, these functions are going to be the same for 224 and 256, but then the output, the security levels, as I said before, dictate the output size. So for 256, we're going to output all 8 integers, but for 224, we're going to stop at this after the 7th one. So 224 goes only up to 224 bits, or that's going to be 7 32-bit words, or 7 integers. And then likewise, when we compare 384 and 512, they're going to be 8 unsigned long longs. For 512, we're going to be outputting all 8 of those values, which is going to be 512 bits, or 8 64-bit words. But for 384, we're only going to be outputting 7 of the 8. All right, let's go into a little more detail on stuff that everything uses. So there are a bunch of functions here. I'm not going to go into too much detail just because it's kind of implementation. This doesn't add to your understanding. All you need to know is that we're kind of combining the data, mixing it around, rotating it, shifting it to get values. And how they came up with this shit, I have no clue. But it seems kind of complicated. But it's when we write it in the code, it's pretty much a one-to-one implementation or one-to-one conversion, as we saw with the SHA1 documentation. So we're going to be taking the pseudocode and just putting it right into C, and it'll pretty much work. Yeah, and then we have different functions for 384 and 512, but it's going to look almost the exact same. It's just we're using different functions. For round constants, 224 and 256 share round constants. So these are going to be our k values that we saw with SHA1. So if we go back here, we had initial k values, and we used a certain k value based on the round, and it's going to be the same thing except for SHA2. We're going to have as many one k value per round. So SHA2 is another round-based hash function, and we're going to have round constants except for 200 for each round. We're going to have a different constant. So for 224 and 256, we have 64 rounds. For the other two, we're going to have 80 rounds, like SHA1. And then with the first two, the lower two, we have this set of constants, this set of 64 integers, and what they are is essentially they detail these as the fractional parts of the cube roots of the first 64 prime numbers. I was trying to look into how this works, but I'm assuming it's going to be the mantissa of like a float representation, but I'm not entirely sure on that. I do kind of want to figure this out because I don't like storing 64 integers and then eventually 80 unsigned 80 long longs when you could possibly calculate it, but I'm not sure. I want to figure that out. All right, so we have, yep, so it's just the first 32 bits of the fractional parts of the cube roots of the first 64 prime numbers. And then for 384 and 512, we have 80 64-bit constants that we'll use for each round. All right, we went through the pre-processing. It's all the same. And then once again for 384 and 512, we're going to have 128 bits reserved for the size. And we're going to split it up into blocks of 1024 bits. All right. Once again, we're going to have initial hash values as we did with SHA1. So our H values, these things right here, these were the initial hash values that we're going to be adding to every time we call the function. So for each security level, there's going to be a different set of hash values. For 224 and 256, these are going to be integers or 4-byte words, and then for the higher two, we're going to have 8-byte words. And today I did actually put them in a paste bin, so I don't have to read them out to you. So yep, 384 has 8 unsigned long longs, and then 512 also has 8 different unsigned long longs. Okay, now we're going to go through the functions. So we have looked at this preparing the message schedule, so that our array W that we looked at here, the two ways to compute it, we had either the array of 80 words, or we can just use a circular array, and we're going to do the same thing here. So we have our message schedule, which is computed using a function here, this thing right here. But once again, the first 16 words are going to be the message, or are going to be the data from the block, or the state. Then we use this function to compute the other values in the message schedule. And then we have our 8 values, A through H, as we saw with SHA1. Oh, that's this kind of stuff right here. And then this is the actual function. So this is going to be for each round, we're going to be computing this stuff. So we compute two temporary values that are computed using a sum, an XOR, and these other functions that we looked at before. Once again, implementation details are not too important. We're going to write them out in C. Another temporary value, a little simpler. And then A through H are going to change. They're going to change each round. And then after each round, we're going to update the hash values, or after each call to the function, we're going to update the hash values and add just the constants that we computed there. And then the output is just a concatenation. All right, so this is the general structure of all four security levels, this right here. I'm going to show you what's different between them, but this is pretty much what it's going to be. We're going to have our message schedule, which will differ, then, but the same thing. The structure is going to be the same. Then we assign our temporary hash values. They're called working variables. Then for each round, we do a set of computations, which I believe will be the same for, or no, this won't be the same for the higher and lower level ones. And then at the end of each call to the function, we're going to update the intermediate hash values using the working variables. And then we can concatenate some or all of the hash values for the output. For 224, it's going to be the same thing, except, like I said, we have different initial hash values, and then we're also going to only be concatenating 7 of the integers for the output. For 512, different constants, different padding scheme. It's just more padding for the length. Our message schedule is going to be different, the computation wise. I believe it will actually. Will it? Oh, it doesn't look like it will. But once again, the schedule is going to be composed of 64-bit words instead of 32-bit words. We still have 8 working variables, but these are going to be, once again, 64 bits. Then we have 80 rounds. This looks the exact same, I think. Could be wrong, though. See, we have that, which is, this is our round stuff. And then afterwards, we're going to update the intermediate hash values using the working variables that we computed in the 80 rounds. And then for the output, we just concatenate all 8 64-bit words. And then for 384, we're going to be concatenating only, it looks like 6 and not 5. Or 6 and not 7. 384. Does that sound right? Oh yeah, sorry. It's for 384. We're going to be concatenating 6 because there's just two less words there. All right, and that's that. So if you watched the SHA-1 video, we went into a really heavy amount of detail on the structure. But if you understand that, this is pretty much the exact same thing. We're just going through it. We're using different variables. We're using different sizes. And then the implementation details are different. But on the upper level, it's the exact same. Okay. I guess we can go into the code now. Before I start writing any code, I just want to let you guys know I committed like 13 commits in the last few days. In the last 3 days, since episode 20, I added utility methods. I added global rotate methods to the C mathematics header file. So instead of having SHA1 rotate word, it's just going to be a rotate word function in the C mathematics header. So all classes, or not all classes, all files can access that. I updated the README, did some stuff. Biggest thing I did was I organized all these files into folders. So now we have different kind of packages that you can do. I added the AES key schedules, forgot to do that before. And then for the SHA3, I finally added the context structure that we looked at for SHA1, where we had this like structure to hold the context, and then we would call 3 methods on the context. So that's uniform now, and then we're gonna be using the same thing for SHA2 as well. And then yeah. So if you want, just take a look at those. Nothing too... the biggest thing was organizing the files and then adding the SHA3 context. But apart from that, everything is pretty self-explanatory. Okay, so let's put away the drawing pad. And let's start writing some code. Alright, what we will do is we will start by creating our header and source files in data hashing. So we have SHA2.h and SHA2.c. And before I forget, I'm just going to add these to the build path. Alright, in SHA2.h, we're going to go ahead and start by including the C mathematics header. And then we're going to do our macros. So if not defined, SHA2h, define SHA2h, and if. Alright, so I put a paste bin link down below, and I have a bunch of constants that I don't want to type out. So just copy these, and I'll go over them real quick. So yeah, it's just there's a paste bin in the description, and only copy the header file once, and then we'll do the source file ones after. So we start by defining our modes of encryption, so 224, 256, 384, 512. Then we define our block lengths. So it's once again, it's going to be most of these variables are going to differ between the two groups, which is just 224 and 256 is one group, and then 384 and 512 are the other group. So we have 64-bit or 64-byte block lengths for the lower levels, and then 128 bytes for the upper levels. We have our output sizes, which are just the security levels right shifted by 3, so going into bytes. I can actually just kind of do this real quick. Hold on. I'm going to make this look fancy. That might work. I hope that works. And then we have our number of rounds, 64 and 80. And then we have our extern arrays for all of our constants and initial hash values. And you see here how the hash values will differ between each of the 4 modes, but the round constants only differ between the 2 groups. And then also we'll see that the size of the words, so for the lower group we have unsigned integers, and then for the upper group we have the unsigned longs. And then before we do anything else, we can just take the source for the array definitions, copy from the paste bin, and then paste that into the SHA2.c. But we first have to do some includes. So we'll just include SHA2.h, include standard.io.h, include stdlib.h, and then include string.h. And we get all those values there. let's hop into the header file. We will do, we'll go through the context. So we're first going to implement it for 256, and then we're going to extend that implementation of 256 to 224, just because we'll see how to integrate the two in a kind of nice way that doesn't take too much extra logic or extra code, and we're not just copying and pasting. But then also, we're not gonna do the 384.512 today or not at all, period. I'll just put it in the code later on just because it's almost the exact same. There's just a few function differences, and you'll see when I put the functions in, it's almost the exact same. It's just using different word sizes. All right, so let's do our context structure first. So we're going to say typedef struct, and I'm going to name the struct for the two modes that we can use it for. So SHA224.256 context, and we're going to name it just SHA224.256 context. In here, I'm going to store the mode just so we can differentiate. Then we're going to have an unsigned long message length, which is just the length of the message, once again 64 bits. Then we have our output buffer. So an unsigned integer h, and it's an array of length 8. And we have our state values, which is just going to be the integer state cursor, and then an unsigned character state, which is just going to be SHA224.256 block length. And then what we can do to make this a little more pretty is we can do two more type defs to kind of add a tag that isn't just SHA224.256, and we can just differentiate between the two. So we'll do a type def SHA224.256 context, and we're going to rename that as SHA256 context just for now. We'll do 224 afterwards as well. But once again, the context just has the mode, the message length, that's a 64-bit word, the buffer, which is just going to be 8 32-bit words, and then we have our state cursor and the state, which is just the block length. Okay. All right, let's do our function signatures now. We're just going to say void SHA256 init context. And here we're going to be passing in a SHA256 context structure pointer, CTX. And void SHA256 update, pass in SHA256 context pointer CTX, and then our unsigned character pointer in as our message, and then integer n for the length of the message. This is going to look exactly the same as SHA1 and the updated SHA3 code, so this is nothing too much. And we have a void SHA256 digest. So we pass in a context and then a reference to an output. So a double pointer, and an unsigned character double pointer. Now we're going to define the function that actually will operate. So we're going to say void SHA224.256f. I'm doing the double name here, just because it's the same. Because I don't want to forget it and then rewrite and then rename everything afterwards. So here we're going to pass in an unsigned integer hash or output buffer array of length 8, and then the state, unsigned character state array of length SHA224.256 block length. And that's it. Alright, so let's go ahead and copy these 4 signatures over to SHA2.c. I'm going to scroll all the way down underneath the constants. And let's start with doing the high level representation. So I'm going to be completely honest with you. Init context, update, and digest look almost the exact same as the SHA1. It's the function that's going to look the most different, and even that doesn't look too different. So I might think of a way to kind of combine the two, but for now I'm just going to do it separately, just because it's easier to teach this way. Alright, so for init context, we have ctx.mode is going to be equal to SHA256. Then we have our ctx.message length is equal to 0. Then we're going to copy over the initial hash values. So memcopy, destination is ctx.h. The source is going to be SHA256h, the constant array that we have up here, this thing. And the size will be 8 times the size, an unsigned integer. And then we set the state cursor to 0. Then for update, this is going to be extremely similar to SHA1. So we're going to start a message cursor, so integer message cursor is equal to 0. Then while that cursor is less than n, so while we still have stuff to read, hold on, there's a fire truck on by. Okay. This goddamn fire department's always messing up my videos. It's not like they have anything important to do. Okay. So we need to determine how many bytes to write to the block. So that's going to be integer number of bytes and block. And this is going to be the minimum. We looked at this last time, so it's going to be the minimum of the block length minus the state cursor, or n minus this message cursor. So SHA224 256 block length minus ctx.state cursor. The minimum of that, and n minus message cursor. So determine whether or not we hit the end of the block or the end of the message first. Alright, then we're going to copy that number of bytes over. We're just going to call memcopy with the arguments. The destination is ctx.state plus ctx.state cursor. The source is going to be in plus message cursor, and the size will be number of bytes in the block. Then we want to advance the cursors. Message cursor plus equals number of bytes in the block, and ctx.state cursor plus equals number of bytes in the block. Alright, then we're going to say if ctx.state cursor is equal to SHA2, the block length, then we know that we have reached the end of the block. So we need to call the function because we have a complete block. So every time we, this is going to be how we pretty much split the block up, or split the message up, without creating that number of blocks. We're just going to, every time we read in a complete block, we're going to call the function on it, which is exactly what happens either way. So we call the function, which is just going to be SHA224 256f. The arguments are going to be h, which is just going to be ctx.h and ctx.state. So the hash, or the buffer for the output, and then the state block. And then we reset the state. ctx.state cursor is equal to 0. And then please don't forget this. After the loop, we need to add the length of the message to this context. So it's ctx.messageLength plus equals n left shifted by 3, which is just length in bits. So we multiply it by 8 to get the number of bits. All right, let's do our digest now. So we have to do our padding first. So the first bit is going to be a 1. So ctx.state at ctx.stateCursor ++ is equal to 0x80. Now, how do I know that ctx.stateCursor is within the bounds? Because if we reached a complete block, which would be the only time it wasn't in bounds, which would be over here, then we reset the state cursor to 0. So it's always going to be in bounds for that last byte to for that padding byte to be written. And then we set the rest of the bits to 0. So memset ctx.state plus ctx.stateCursor, and it's going to be, the value is 0, and the size will be the maximum of SHA, the block length, minus ctx.stateCursor, and 0. So this is just, we never want to set a negative value, but this could also be 0. So if this was the last byte, so if we just set the last byte of the block to 0x80, then the state cursor is going to be the block length. So we're going to be setting no bytes to 0. And then we need to output the size. But first we need to determine if we have enough space to get the size. So if ctx.stateCursor is greater than or equal to SHA, the block length, minus the size of an unsigned long. And if it is, then we need a new block to write the length. So we're first going to call the function since we have a complete block. So it's going to be SHA224.256f, passing in ctx.h and ctx.state. And then we need to reset the state. ctx.stateCursor is equal to 0. And then memset ctx.state 0 block length. So after we have called the function, we need to reset all the bytes to 0 since we need an empty block. So it's almost as if we just padded the whole block with zeros, which is what the algorithm calls for. But we need to set the whole block to 0 before putting in the length. And then we need to set the last 64 bits as the length. So make sure that we're doing this outside of this if statement. So the if statement was to determine if we needed a new block, and now that we have determined if we do or don't, then we can now set the block, or set the, or put in the length. So we're first going to get a temporary variable, unsigned long size is equal to ctx.messageLength. Then for integer I is equal to 512 right shifted by 3, or this should be the block length right shifted by 3. Minus 1. So once again, the way memcopy worked with the long was kind of weird. I'm not entirely sure how it works, but we essentially have to output byte by byte, which sucks. So I starts at the block length right shifted by 3, that whole thing minus 1. Then we go while size has a value, and then I minus. I'll explain the condition in a second. Then we want to set the least significant byte on the rightmost slot. So ctx.state at I is equal to size. So it gets the least significant byte of the long. And then size right shift equals by 8. So remove ls, the least significant byte. So we're essentially copying the long in small endian order, or small endian by byte, but big endian by bit. So that's why we're doing this, yeah. So, and then we right shift to remove it, and then if we ever get a 0, then we don't have any more values to set because we have already set the rest of the block as 0, either here or here. And then we just don't need to write anything if we only have 0 left. And then we need to call the function on the last block. So it's going to be SHA224 256 f passing ctx.h and ctx.state. And then we reset the state. ctx.state cursor is equal to 0. Alright, and now we output. So output is the array. So we're going to be outputting the concatenation of the array, of the H array. So we first need to allocate. So dereference of out is equal to malloc SHA256. Now make sure you are using the 256 constant here. Out, because it is different for all 4. Times the size of an unsigned character. Then if not the dereference of out, this is just an error check to make sure we allocated memory. Return. And then we write. So for integer I goes from 0 to 8, this time not 5. I++. Then for integer j is equal to 3, j is less than, or j is greater than or equal to 0, because once again we need to write it in a specific way. J minus minus, count down. Well, let me make sure. Yeah, okay. Make sure in the other loop that we had, where we output the length, make sure that the incremental step is I minus minus. But here we're going to have I goes from 0 to 8 plus plus, and then j goes from 3 to 0 minus minus. Alright, then for each iteration, we're going to get the least significant byte on the right side. So we're going to dereference out in parentheses, and then get the character at I times 4 plus j, and set it equal to ctx.h at I, and that's automatically truncated. And then ctx.h at I, right shift equals by 8. And this removes the least significant byte. Alright, and that is the high-level description of that function. Now let's actually write the function that is the basis of this whole thing. Once again, this is going to look awfully similar to the SHA1 f function. Alright, so we start by initializing our word schedule. So we have an unsigned integer w, array of length 16. And this is going to be a circular array. So what the algorithm calls for is that we initialize AD values in our message schedule, or 64, sorry. Yeah, over here. But using some clever tricks, we can kind of model this convert this linear array into a circular array, because to compute every future value, we only need the last 16 values. So if we just keep this array like this, then we have all the values that we need to compute the future values. We don't need to just compute it as 64 integers. So the first part of this, or the first iteration of this array, is going to be the message itself. So for integer I goes from 0 to 16, I++. Then for integer j goes from 0 to 4, j++. Then we need to say w at I left shift equals by 8, and this is increasing magnitude by 1 byte. Once again, memcopy should do this, but I don't know why it doesn't for some reason. Like, it should do it like this, but no, that's wrong. Memcopy should not do this. It should be copying the least significant byte to the least significant byte, which is what it does. But it's weird because we have a state array, so the least significant byte should be the leftmost byte in each word. I explained how this works last time. So yeah. Then w at I bitwise or equals state at I times 4 plus j. So we copy in the byte. Yeah. All right, then we initialize our function variables. Now, instead of having 8 different integers a through g, I think, or A, B, C, D, E, F, G, H. Instead of having a through h as different variables, I'm just going to have an array of 8 integers. So it's going to be an unsigned integer array h2 of length 8. And then to initialize them, we just need to go I goes from 0 to 8. And we just set so I'm actually going to call these the working variables. So the initial value of each working variable is just going to be the h array that we pass in. So we're just going to be copying. We can actually just, why do I do this? We can just copy it over. Memcopy destination is h2, source is h, and the size is 8 times the size, an unsigned integer. So the working variable, once again, is just the copy of the array. All right, now let's go through the rounds. So for integer t is equal to 0, t is less than SHA224 NR for the number of rounds, t++. All right, then we calculate our reduced index. Int s is equal to t, bitwise ANDed with 0xf, which is just mod 16. Then we're going to calculate our new word if t is greater than or equal to 16. So if t greater than or equal to 16, then we're going to calculate the next word in the word schedule. The reason why we need this condition here is because this first 16 values will be the state. So we already copied in the first 16 values. So we only want to calculate new ones if t is greater than or equal to 16. So we're going to get indices first, so we don't have to recalculate them all every time, because the way this one works is we get the same value 3 times and then rotate it or shift it each time, but it's the same index every time. So we're going to say integer IDX S1 is equal to S minus 15, bitwise ANDed with 0xf, and then integer IDX S2 is equal to S minus 2, bitwise ANDed with 0xf. Now we're going to, or wait, sorry, this should be IDX S0 and S1. Now we're going to calculate our values S0 and S1. So an unsigned integer S0 is equal to right rotate I. This is a new function in C mathematics.h. Does this? It pretty much does it, but it just it does what rotate word did in SHA1, but it just goes the other way. Because we're trying to go to least significant bit now. Alright, so we right rotate I, and the value to rotate is going to be, or sorry, let me make this a little simpler. Instead of having the indices, I'm just going to get the values since we retrieved them 3 times. So we'll say unsigned integer val s0 is equal to w at s minus 15 bitwise ANDed with 0xf. Yeah. And then unsigned integer val s1 is equal to w at s minus 2 bitwise ANDed with 0xf. And then for s0, we call right rotate I on val s0 and rotate it by 7 bits. XOR that with right rotate I of val s0 18 bits, and then finally XOR that with the value, so val s0 right shifted by 3. And then s1 is going to look kind of similar. Unsigned integer s1 is equal to right rotate I val s1, and we're going to rotate that by 17 bits. XOR that with right rotate I val s1 by 19 bits, and then XOR that with val s1 right shifted by 10 bits. So this is what it should look like. We have 2 rotations and then a shift for each s value. So we have 2 s values now, and then for the next word in the word schedule, it's just going to be w at s is equal to w at s plus s0 plus, now w at s minus 7, that in parentheses, bitwise ANDed with 0xf to reduce it, and then plus s1. So once again, these are the implementation details that you saw in that document, but they're not too important. Well, they are important because they make up the algorithm, but it would be pointless for me to be like, oh, so for S1 you do this, explain it, and then write the code separately when I can just explain it while I'm writing the code, because I have no clue how this increases security. I think it's just shuffles the bits around strategically. I'm not that, I don't know that much about math and computer science to know how this all works or why this is proper or secure. I watched a video on SHA-3. That's how I initially got into the hashing shit. And the dude said, why do we use these values? Well, because they're secure. But I have no fucking clue why they're secure. I'm not hating on the dude because the video was fucking amazing. I think it was called Christoph Parr, or Introduction to Cryptography by Christoph Parr. Great series. That introduced me to AES and SHA-3, which is pretty much where I got my material, or not my, pretty much where I got my material from. I didn't get the code from him because that's an encryption course. That is not a comp sci course. That is a data security course. They go over the mathematics of that. But he did just say, we use these values because they're secure, but I have no fucking clue what that means. Okay, so now we've calculated the word schedule, and let's go through each round now. So we did the message schedule, and then now we're going to do the round function. So we're going to have 6 values. Unsigned integer S1 is equal to right rotate I. We're going to rotate H2 at 4, which is E, I believe. We're going to rotate this by 6. XORed with right rotate I H2 at 4 by 11 bits, and then XOR that with right rotate I H2 at 4 by 25 bits. Then we have unsigned integer CH. I'm just getting these names from the documentation. This is equal to H2 at 4. So we're going to do just in parentheses H2 at 4. Bitwise ended with H2 at 5. That XORed with the complement of H2 at 4. Bitwise ended with H2 at 6. I can zoom in real quick too. So once again, S1, or let me just do this, the combination of this, and then I'll go over it again. Or I'll just do all 6 and then I'll go over it real quick. Then we have unsigned integer S0, or sorry, TMP1 is equal to H2 at 7. So that's H, I think, plus S1 plus CH plus the round constant, so SHA22426 underscore K, that array at T plus W at S. So we're adding the current round constant for the current round plus the corresponding word schedule, or the word in the schedule. Alright, then for a second temporary value, we have unsigned integer S0 is equal to right rotate H2 at 0 by 8 or 2 bits, XORed with right rotate, this should be right rotate I, make sure the functions are proper. The value is going to be H2 at 0 by 13 bits, and XOR that with right rotate I, H2 at 0 by 22 bits. Then we have our major, so unsigned integer major is equal to, we're going to do this in 3 different sets and then XOR them, so it's just H2 at 0 ANDed with H2 at 1, the second term will be H2 at 0 ANDed with H2 at 2, and then the third term will be H2 at 1 ANDed with H2 at 1, or H2 at 2. So at 0, XORed with at 1, or sorry, not XORed, ANDed with. That term XORed with H2 at 0, ANDed with H2 at 1, or at 2. I'm realizing now I should have done this in letters because this is a lot, that would be a lot easier to say. I mean, I could just convert them. So we have, I'll do that when I go over this, but let me just finish writing the code and then I'll once again go over it. So then that XORed with H2 at 1 ANDed with H2 at 2. And then we have unsigned integer TMP2 is equal to S0 plus major. Alright, let's shuffle the values and then I will go over it real quick. So we have H2 at 7 is equal to H2 at 6. H2 at 6 is equal to H2 at 5. H2 at 4. H2 at 5 is equal to H2 at 4. H2 at 4 is equal to H2 at 3 plus TMP1. H2 at 3 is equal to H2 at 2. H2 at 2 is equal to H2 at 1. And then H2 at 1 is equal to H2 at 0. And then H2 at 0 is equal to TMP1 plus TMP2. I feel like I can make this a little better. Let's do a loop, actually. So for integer I is equal to 7, I is greater than 0, I minus minus. So what I'm going to do here is I'm going to do a loop from 7 to 1. And I'm just going to initialize all the working variables as the one right before it. So h2 at I is equal to h2 at I minus 1. And this does not overwrite anything because we're working downwards. So we access the value before we overwrite it. And then I want to set different values. So h2 at 4 plus equals TMP. And then h2 at 0 is equal to TMP1 plus TMP2. Sorry, h2 at 4 should plus equals TMP1, and then h2 at 0 is equal to TMP1 plus TMP2. So it should be self-explanatory how these two are equivalent. If we didn't have any additions here, it would just be a shift upwards of elements in the array. But since we do have additions, we're going to do the shift first, and then we just add the values to the two indices that we need. So that takes care of all that. All right, let's go over this stuff. So let's look here. I really wish I could zoom out in the sidebar and not the code. Okay, S1 is a function of E, or h2 at 4. So I will just call h2 at 4 E now. So S1 is right rotate of E by 6 bytes, XORed with the right rotate of E by 11 bytes, and then XORed with right rotate of E by 6 bits, 11 bits, and 25 bits. CH is a function of E, F, and G, so H2 at 4, H2 at 5, and H2 at 6. So we're just doing E and F, that XORed with not E. I'm just going to read it off here because it's a lot simpler. Oh wait, it's separated, so I can't. I guess I have to do this here. So then we have not E, ANDed with, this should be an AND. Make sure that's an AND there. Not E, ANDed with G. Then we have TMP1, temporary 1 is, that's going to be H, plus S1, the sum that we calculated up here, plus CH, plus the corresponding round constant, so index T, plus the corresponding word schedule value, so index S, which is just the reduced one for the circular array. All right, now for our second sum, this is going to be a function of A, or H2 at 0. So we right rotate A by 2 bits, XOR that with A right rotated by 13 bits, XORed with A right rotated by 22 bits. And then the major is going to be a function of A, B, and C. So we have A and B XORed with A and C, XORed with B and C, so just the 3 combinations. And then TMP2 is just this sum 0 plus the major. And then we shuffle our values around. And that is, in essence, each round. Okay, and then after the round loop, we're going to update the, not the hash values, the buffer values. So we're going to do a loop for integer I is equal to 0, I is less than 8, I plus plus. And we have h at I plus equals h2 at I. So to update the hash values, we're simply just adding the working variables. And that is SHA256. So let's go ahead and take an example. I put a test suite down below. It's the official NIST test suite. And there's just test values for all different types of encryption things. I forget where it is. Hold on. Let me pull it up. It's the test vectors link in the description. All right, so it's this page, and we're going to be looking at secure hashing. So we see that we have SHA-1, their test values, but we're going to be looking for SHA256. So our input sample here is ABC. And what we can actually do is, as a little, to kind of make it more like this, I will kind of go through what this does. So ABC, or let me actually just go into main.c first and type out how this process is going to work. So we have SHA-3. I'm going to organize this main function a lot better. But for now, I'm just going to comment everything out. So for SHA-2, or 256, we're going to say the message is equal to ABC. Then we're going to initialize our context, so SHA256 context. Oh, I need to include it first. So include /c mathematics /data /hashing /SHA2.h. And then we have our SHA256 context, which is going to be CTX256. Then SHA256 init context, passing a reference to CTX256. Then SHA256 update, reference to CTX256. The message will be message, and then the length will be 3, since there's 3 characters, so 3 bytes. Then we have SHA256 digest, passing a reference to CTX256 and a reference to hash as the output. Then we're going to print out our hash using print byte array. So out is equal to print byte r, passing the hash. The number of bytes would be SHA256 out, null, and 0, 0. And then printf SHA256. I'm just going to print out the string. And then free out, free message, and free hash. So this is how we're going to implement it essentially. Hold on. I don't know. Never mind. This probably looks very confusing, but this is our main.c file. You have a message, get the context variable, then we initialize the context, update the context with the message, digest it, and then to the output, and then we're just printing out the output here. That is not right. Uh-oh. All right. I don't think that doesn't look right. That is most certainly not right. Okay. So let's go into SHA256F, and we're going to kind of do an output that's like this. So we're first going to print out the hash values. So printf hash values for integer I is equal to 0, I less than 8 I plus plus, printf h at some value is equal to another value. And I'm going to print out an integer in hexadecimal. You can actually do this really nicely in the printf function. So it's going to be 0, 8, L, or 0, 8, LX. So the 0 represents the padding, or the character to pad. 8 is the length. L means long, or a 32-byte word, a 32-bit word, and then X means in hexadecimal. And then the value to print will be I, and then H at I. All right, then we're going to do the same thing for W. We'll print out I and then W at I. And then after each round, what we're going to want to do is we need to print out the working variables. So printf I feel like this might be the problem, this little shifting thing. I'll test it afterwards, but let's just print out the values to see what comes up. All right, so I have, let me just make this full screen. So we have that we're going to be printing out the hash values first. Just print out each hash value by value, and then we have our block contents, once again, each of the words separately, and then after each round, we're just going to be printing out the row of the working variables. I really want to put a context window on the right side, but I can't do that. What? Nope, that didn't work. I need more space. Oh, wait, because I didn't do a new line. That's why I'm an idiot. \n. All right, 63 rounds. Okay, let me just do a new line afterwards too. Just make this look pretty. All right, so we have our initial. This might be the problem, is it? Yeah, that is the problem. Oh, so we're padding the wrong. We're putting the length in the wrong spot. Where are we putting it? All right, digest. Oh, okay. So I don't need to right shift the block length by 3. Okay. So in digest, when we are setting the last 64 bits as the length, do not right shift the block length by 3 because that's already in bits, or that's already in bytes. You don't need to put it into it's not in bits, and we need to put it into bytes. It already is in bytes. And there we go. So it did work. Everything did work properly. And we have this little nice output here that we can kind of compare to the NIST test suite with, which is pretty cool. Okay, so I'll just zoom in real quick here for you guys. Okay, so that is SHA256, and now I'm going to show you how to integrate, or just pretty much use this code with a few modifications to make SHA224 work. I'm not going to do 384 and 512 today because that's just, it's going to be the same process pretty much, but I will put it on the GitHub. So for 224, we're going to use the same context because it has the same values. We're just going to update the mode differently. Message length is still a 64-bit word. So we still have 8 buffers, 8 buffers. 8 words is the buffer. Still have a state cursor, and the block is the same length. We're going to add a new type def here. So type def SHA224 256 context, SHA224 context. So we can differentiate the two. Because this, honestly, 224 context looks better than 224 256. It's more specific. All right, so we're going to have the same 3 functions, the initialize, context, update, and digest, with the 224 label, obviously. So we're going to say void SHA224 init context, pass in SHA224 context pointer CTX, and forward SHA256 or 224 update, pass in SHA224 context CTX, and then forward SHA224 digest SHA256 context or 224 context pointer, and an unsigned character double pointer out. And then make sure to have the other parameters in update as well. So the parameters are the exact same, literally, because the 224 context is the same as the 256 context. They're both the same structure. Now let's look at what code we need to reuse and what code we need to put in a different function. So we'll go to SHA2. And let's do a quick recap. What is different between 224 and 256? If we look at the constants first, we have the same round constants, so that's fine. The initial hash or the initial buffer values are different, so we're going to have to create, we can't reuse the 256 initialize context method. So let's just write that now. We first have to copy the signatures over. So for 224 initialize context, we're going to set the mode, ctx.mode is equal to SHA224. Then ctx.message-length is equal to 0. Then memcopy, destination is ctx.h. Source is going to be SHA224h. And the size will be 8 times the size of an unsigned integer. And then set the state cursor to 0. So ctx.stateCursor is equal to 0. So that's different. Now for update, what is different? We have our message cursor, which is going to be the same. We're going to go until we get to n. The block length is the same. There's nothing in this method that is exclusive to SHA256. We can look at it. This constant here is 224, 256. State cursor is the same. Number of bytes in the block will be the same. We have our constant here, 224, 256. And then when we reach the end of the block, we call the function f. But the function f is the exact same for both the security levels, because the only thing that could be different in this function is the state constant, but that's the same. The state constant k here, this thing right here, k is shared between 224 and 256. So this whole function here, I named it 224 256 for a reason, because it's just going to be the same. So for update, we can actually just create a shared update function named, it's going to be return type void, SHA224 256 update, passing a SHA224 256 context pointer, I'm doing the combine name now because this is for both functions, or both algorithms. And then we pass an unsigned character pointer in and an integer n. And then I'm going to take SHA2.c and I'm going to rename SHA256 update to 224 update. And then update the parameters as well. And then we're going to move this function down below. Now for the update method, we have to do the SHA256 update as well because we need to have a definition for it. What is it going to be? Like I said, it's the exact same. So all we need to do is just call the function. We're just going to call SHA224-256 update, pass in the context because these two context, SHA256 context is a SHA224-256 context. So we can just pass in the parameters as is, in and then n. And then the same thing for SHA224 update. It's going to be the same stuff. Just call SHA224-256 the combined update method with ctx in and n as our integer. What's up? There we go. Okay, we're all good. Now let's look at digest. Padding is going to be the same. The constant here is shared. The block length is shared. The function is shared. This is shared. The setting the length, that's shared because they're both 64 bits. Now the one we call the function, that's the same. Reset the state, good. Now the only thing that's going to be different now is the size of the array. Size of the output and then the output itself, because once again we're only outputting 7 of the 8 words to SHA224. So we are going to create a shared digest function. It's going to be void SHA224-256 digest, and we're going to pass in the shared context as a pointer, but no other parameters, because we don't want this function to output to anything. I mean, we could, you know what, let's do it to make it simple. We'll have an unsigned character double pointer out, and then we also have, because we need to pass in 2 extra parameters that are based on the output. The length of the output, this thing right here, that is in the mode. That's stored with the structure. That's this value right here. So we're good there, because hold on. Yeah, we are good. That is fine, yeah. Because we can just right shift it by 3. But we do need to pass in the number of words to concatenate. Or, you know, we'll actually just pass in both, or we'll just pass in the out length. So integer out length as a parameter there. So we'll copy the signature over into SHA224.c or SHA2.c. And then what I'm going to do is I'm going to take the existing definition, or the existing function body for SHA256 digest, and I'm going to copy it over. I'm going to cut and paste it. And we'll look at what we need to change. Okay, so for digest, we have our padding. It's the same for both. So we can skip that. Call the function, same for both. Reset the state, same for both. Now, the output array, we now need to differentiate between the size. So we're going to pass in the out length as a parameter. So when we call malloc for the output array here, instead of using the macro, we're just going to see out length as the number of characters to allocate. And then for the loop here, I'm going to create another variable, integer number words is equal to out length divided by the size of an unsigned integer. So this will get the number of integers to output. So for 224, that's going to be 7 integers. And then for 256, that's going to be all 8 integers. So number of words. And that should be it, because H, we still have the same H values in the context, in each context, and it's going to be like that. Good stuff. I'll just do that there for a second, actually. So once again, in our shared digest function, the thing that changes is we have an extra parameter called outLength, which will be the number of bytes in the output. Out here we'll call malloc on outLength, or malloc with allocating outLength number of bytes, and then we get the number of words by dividing the outLength by the size of an integer, and that will give us the number of integers to actually write to the output. But the copying stage is the exact same. All right, now we can update our digest functions for the individual security levels. So for 256 digest, we're just going to call SHA224 256 digest on CTX is going to be CTX. The output will be out, and then the out length will be SHA256 out. We're going to be passing that macro in as a parameter. And then similarly for SHA224 digest, we're going to call SHA224 256 digest. The context will be CTX, the output will be out, and then the out length will be SHA224 output. And good stuff. Good shit. All right, let's head into main.c now, and we're going to test this out. So let me get a test vector for SHA224. If our message is ABC as well, so we can just use the same ABC. So we'll do the exact same thing. So SHA224 context, CTX224, SHA224 init context, passing a reference to CTX224. Then SHA224 update, passing a reference to CTX256, message, and 3 for the number of bytes. And then digest. So SHA224 digest, passing a reference to the context for 224, and the output will just be a reference to hash, and then we'll print it out the exact same way. Except just make sure not to free the message before doing SHA256. Because we need to use the same thing. Alright, so let's run this and hope there's no errors. Oh, I need to get rid of the printing. Yeah, that makes sense. Alright, so 224 produces this, 256 has the same output, so we know that the function still works, it's still compatible. So we need a 2309, which for we get. Good stuff. We have a 2309 7022. 2309 7022. Okay. Alright, so that was fun. I'm going to be honest, that's pretty much all I had for you guys today. I will be adding the 384 and 512 modes soon, at some point, when I get the time. But so this should be, we're kind of after this, I think we're done with hashing. And then I'm going to get onto applications of the hashing. So the HMAC algorithm, the PBKDF2 algorithm, which I want to use to develop a password application at some point. But yeah, that's all I have for you guys today. Hope you guys enjoyed, and I will see you guys next time. Have a good one.